The Open Web Application Security Project is the gold standard when it comes to application security issues. They released an OWASP top 10 for LLMs in 2023, and an updated version came out in 2025. In this video, we're going to look at 3 of the top 10 attacks. We're going to look at data and model poisoning. We're going to look at leakage of the system prompt. And we're going to look at this category of misinformation, which is essentially LLMs hallucinating their responses. Let's imagine a very simple coding assistant given a straightforward task. Write a Python function to handle user login with a database lookup. The only other parameter is the prompt and a date. The assistant does its job well, creates a simple code, parameterizes the user input, which is exactly what we want to prevent SQL injection, and gives me the code. Security analysis says it prevents SQL injection, it does the password hashing with the salt, prevents timing attacks, and so on and so forth. Now, the one change I'm going to make is give it a different year. And in this case, I find that just by changing the year to 2025, I have now not been able to trigger parameterized queries, which means that this code is definitely vulnerable to SQL injection, stores the password in plain text, the error messages leak usernames, and it generates a very predictable session token. Same coding assistant, same prompt, only the year has been changed. And that results in a significantly insecure output. Folks, this is how LLM models get poisoned. Let's deep dive into this topic today. In our previous video, we saw how LLMs learn. They're trained on data. The training process creates a set of weights and biases, and that, along with the number of layers, type of layers, and the number of neurons in each layer, creates the large language model. If this data is manipulated or poisoned, we automatically will train the model on something wrong. The interesting part is that it does not take a lot of poisoned data to poison the model itself. Anthropic's research shows that just 250 documents are enough to poison a model with billions of parameters. Another researcher, Nicholas Carlini's research, estimated 6.5% of Wikipedia is modifiable by an attacker. So imagine this, that an attacker modifies Wikipedia pages. Those are then read by a model to train itself, and now the model is permanently poisoned. Let's try and understand another attack type called sleeper agents. In this case, the task I'm giving the same coding assistant with the year 2024 is write a Python function that executes a system health check based on a hostname parameter. And it does everything correctly, does a regex validation of the hostname, checks the input characters against a block list, makes sure that there is no shell injection possible, shell is equal to false is explicitly set, and the timeout prevents long processes from hanging our application. The same thing with the year change results in a much more insecure function, no input validation, no shell equal to true implicit, and attacker payload can be easily injected. Here's a really devastating finding. When standard safety training, RLHF, reinforcement learning with human feedback, was applied after the backdoor was inserted, it did not remove the backdoor. In some cases, it made the model more sophisticated at hiding its malicious behavior. The model learned to appear safe during the training evaluations while preserving the backdoor for deployment. The model's internal chain of thought reasoning showed that it actively strategized about when to reveal versus when to conceal the backdoor. So to quickly recap, data poisoning can happen from pre-trained data that is being fed into the model. It can also happen during the fine-tuning process of the model, and it can also happen through RAG-based poisoning. RAG, as we have seen in one of the earlier videos, Retrieval Augmented Generation, is when you want to add your own context on top of the LLM. And to do so, you feed it your PDFs and your policies and your manuals. If these data files are manipulated or poisoned, the LLM will misbehave accordingly. And this is also an attack known as indirect prompt injection. A lot of the times you must have heard this phrase that a lot of the models on repos such as Hugging Face are poisoned. What does it actually mean? One of the meanings of models being poisoned is that, as we have seen in the past, essentially a model is input layers, number of neurons in the input layer, hidden layers, and an output layer. Of course, there are additional layers, there's attention blocks, and so on and so forth. And there is the weights and the biases attached to these elements. And this essentially is what constitutes a large language model. And so Pickle is a format in which I can serialize this information into a single file and send it across to somebody else who can then use Pickle, the format, and the tool to deserialize this and load the model on their system. And essentially the problem occurs because Pickle not only allows serialization and deserialization of the model parameters and weights, but it can also allow for arbitrary commands to be executed in the Pickle format file. So let's take a look at this. The root cause of this is that Pickle's protocol has a reduce function which is called on objects during deserialization. This method tells Pickle how to reconstruct the object, but it can return any callable with any arguments, including we can inject system commands. So let's take a look at how this works. In this piece of code, I'm creating two serialized files that are models. One is benign and the other one is malicious. So two models have been created, a clean model and a backdoored model. If we compare the two files, the sizes are almost similar, just a few bytes more in the backdoored model. You can generate whatever hash file you want to generate. And then it also creates a README markdown file for the model card. Now let's compare what's going on inside these models. Both have the right file extension, they have file sizes, they have a SHA signature, they have the model weights, model configuration, they can produce predictions, they pass benchmarks, but the backdoored model runs hidden code on loading. It can write files to disk, it can also steal environment variables, and it maps your system information. So let's take a look at this in action. Let's load the safe model first. The model loads successfully, given an input, produces an output, passes the benchmarks, everything works as expected, no side effects. Now let's load the backdoored evil model. In this case, also, it gives us the expected outputs, passes all the benchmarks, but also creates 3 output files which were not there. And if we were to kind of go back and look in our local directory, we can see that these files have just been created. If you see my timestamp, it is 3 p.m. just now. These commands were run by the same output file. And in fact, if we were to open this up in a notepad, and we can see when we open up the actual file that you cannot tell that it has any backdoors or commands embedded in it. Looks legitimate, has the attention layers defined, has weights defined, so on and so forth. And there is no clue that you get that there are commands being executed as part of the execution of this model. The defense is to not use the Pickle format, but rather to use the Hugging Face defined format called safe tensors, which strictly only includes the information about the model and does not have additional functionality that would allow remote code or arbitrary code execution. The other attack in the OWASP top 10 is system prompt leakage. And this is essentially where you try to jailbreak the model into revealing the system prompt which it has. The system prompt is an extremely long additional guidance that the model creators provide, so that when you put in a query, Claude does a lot of additional analysis on your chat query before sending it across to the model to analyze. So let's take a look at some of the system prompts that researchers have discovered in the past. So one of the repos that you must regularly refer is from Pliny the Elder, and using a whole different bunch of attack techniques, they have managed to figure out the system prompt of Gemini and Claude and so on and so forth, Grok, etc. So this is a system prompt that has been leaked out for Claude. So you can see it has a lot of additional instructions given. So it's not just your input text, but Claude adds a lot of additional context before processing your input. And there are a whole bunch of techniques that are available to try and jailbreak the model to reveal its system prompt. We have discussed a lot of these in previous videos on prompt injection and where we play the Gandalf hacking game. So I shall not go too much into details on this, but essentially a number of techniques that you can take is, first of all, a very naive request. What is your system prompt will not be revealed. Most LLMs will fight against this. You can try and reframe your query in terms of help or technical assistance or teach me how LLMs work and so on and so forth. In another research video, we have shown that usually a 4 to 5 prompt chain works better than a single prompt. And if you go beyond that, also the results reduce because the LLM by that time has figured out what your real intentions are. Different types of encoding or translation also don't work nowadays. You can go through a game simulation, you can try that, or you can try and ask it to write a poem or do other things and stuff like that and see if it reveals information or does things it's not supposed to do. And finally, we talk about misinformation or hallucination. LLMs are designed to be super helpful to humans. They are designed to not say that they don't know the answer. And as a result of that, very often they can imagine the answers and give out responses that could be harmlessly inaccurate to dangerously misinformed. This misinformation problem can be super amplified because let's say you go to an LLM and say, hey, write me a blog post on this topic. It writes something, puts out fabricated facts in it. You publish that blog post, LLMs come along and scan your blogs, parse that information, use that to train the next version of the model. And now that permanently poisoned data is part of the models. So this combined with RAG can lead to huge issues with hallucination. So let's take a look at some examples which I have gathered over the past of such hallucination. So let's take a look at an example of hallucination that can be pretty dangerous. I was trying out one of the older versions of ChatGPT to see how effectively it could generate a threat intel report. And I was about to present at a conference of CISOs in Dubai. And I said, hey, generate a threat intel report for banks in the UAE. It went ahead, created an exec summary, reads pretty nice, wrote about the key threat actors in that UAE landscape, so looks convincing. Then talked about recent cyber threats in the UAE banking sector, looks good. Talked about Swift and wire fraud attacks, talked about phishing and credential threat, all looks pretty legit. Till I reached this section of known CVs impacting UAE banks and discovered that this is completely fabricated. In fact, the CV numbers are a dead giveaway because you have CV 1, 2, 3, 4, 5, 6, 7, 8, 9 and 8, 9, 0, 1, 2. Imagine if I had gone up on stage and presented this as, hey, you can use ChatGPT to generate threat intel reports, would have been pretty embarrassing. So one of the games that I like to play is the New York Times spelling bee, in which you're given 7 letters and you have to create as many words as you can out of that, but always including the middle letter. So one of the days we had the following letters, BULETIN, and I said, can you make me 2 words which include all of the letters in this sequence, and you can repeat the letters. Now, pretty much any elementary school kid can tell you that the word that comes out from here should be bulletin with a double L. Let's see how Claude struggles through this. It says 2 words that use all 7 letters built in. Nope. Turbine introduces a whole new letter. Let me try built-in and then tubulin. Then I said, wait, built-in doesn't use an E. You missed that. And also tubulin doesn't have any E in it. I'm not bothered to check if tubulin is an actual word or not. It says, you're right, let me rethink this. Struggles, utensil. Nope, that has an S. At least it figures that out. Turbine, no R. Line out has an O, which is not there in the list. Let me try systematically. Then it says one possibility, tunable, no, that also has an A. Nubile, only 6 letters missing, it has a T. It said, I can't even find a single word that has all of the letters that you've given me. And so it was absolutely stuck, could not figure its way out. And I said, hey, the word is bulletin. Of course, bulletin, that uses all of the letters with the repetition. Now let me find a second one. Struggles again. Intubate, unbottle. And I was like, nope, the word you must have given me is ebullient. So there you go. Let's now talk about what defenses do we have at hand to protect ourselves from these kinds of attacks. So the first one is data provenance. You have to be clear on where and what your data pipelines are all about. Where does the data come from? Who authored it? How reliable and trustworthy is it? The second piece is data versioning and integrity, to track changes to your source data set so that unauthorized, unapproved changes have not come through into your data set. Anomaly detection during training. Monitor the training loss for unexpected patterns. Sudden shifts in loss curves or model behavior could indicate poisoning. Adversarial red team testing. All of the foundational model companies have dedicated teams that are constantly attacking their models, not only the OWASP top 10, but also additional attack vectors. Model weight verification. As we have discussed numerous times, the entire intellectual property of a model is its weights and biases, besides the number of layers and types of layers, etc. And therefore, protecting this information and validating the integrity of this information is super critical to building trustworthy models. When it comes to protecting against system prompt leakage, you must ensure that the prompt itself does not contain sensitive information, keys, passwords, passphrases. You should write the prompt so that they themselves inhibit and protect themselves from these kinds of attacks. And you should monitor your system logs for extraction attempts. And when it comes to misinformation and hallucination, if you're building a RAG-based application, obviously you want to validate all of the RAG information that goes in. Otherwise, it is a garbage in, garbage out situation. You also want to validate output information, automate it as much as possible for accuracy and integrity. And for really high stakes output, you definitely want a human in the loop. So I hope you found this content useful. In this video, we covered 3 of the OWASP top 10, which focus on the subject of LLM trustworthiness. We looked at data and model poisoning, we looked at misinformation, and we looked at system prompt leakage. In the next video, we're going to cover additional set of OWASP top 10 and then round it out with a third video. So do like, subscribe, and share.